Hi, welcome back to our Azure Pipelines containerized agent series. In the previous video, we've built containerized agents, evolved pipelines with matrix deployments, and developed templates for maintainable CI/CD. However, there's one challenge we have not addressed. Our Docker agents are ephemeral. Every time a container restarts, everything's gone. Build caches, downloaded dependencies, artifacts. That's supposed to be a feature, right? Fresh environments every time? Well, yes and no. Today, we're adding persistent storage to our Docker agents. Think of it like a USB drive that you can plug into different computers. The data stays with you even when you switch machines or containers. By the end of this video, you'll understand when to use persistent storage, how volume mounts work, and see in action an Azure Pipelines agent build an artifact that another agent can use to deploy, all without uploading to Azure Pipelines artifact storage. Let's dive into the world of persistent storage. First, let's understand the problem. Docker containers are ephemeral by design. That's one of their biggest advantages. Turn off a container and you get a completely fresh environment. No accumulated rubbish, no mysterious leftover files. But this creates challenges in some CI/CD scenarios. In build caches, your agent downloads dependencies every single time. There's no npm cache, there's no Maven local repository, no Docker layer cache survival between restarts of your container. Artifact sharing. In our matrix deployments, if Agent 1 builds an artifact and Agent 2 needs to deploy it, Agent 2 cannot see what Agent 1 built. They're running in isolated containers. Unless, of course, you use the Azure Pipeline storage. There's performance impact. Repeatedly downloading the same dependency wastes time and bandwidth. This is especially problematic in enterprise environments with large code bases and some even with restricted internet access. You might ask, why not just use the Azure Pipelines hosted artifact storage? Well, there are scenarios where you need full control over large files that are slow to upload or download. There could be security requirements where artifacts must never leave your network or bandwidth constraints in remote locations. Today, we'll solve this with Docker volume mounts. Think of them as shared folders that outlive individual containers. Docker offers several types of persistent storage, and the key ones are, the first is bind mounts. It's where you mount a directory from your host file system directly into the container. It's easy to access from your PC, but ties you to specific host paths. So it's important to note that it is not portable across different OS types. The second type is volume mounts. These are Docker managed storage that lives inside Docker's world. The Docker daemon controls it, and your host OS doesn't need to access the data. In fact, you cannot access the data. For this demo, we'll use volume mounts. This is the recommended approach. Here's why. Docker controls the storage location and lifecycle. There's better performance, especially on Mac OS and Windows, where Docker Desktop runs containers in a Linux VM. Yes, on your Mac or Windows VM, Docker Desktop runs containers in an underlying Linux VM. The host, when we're talking about it, is not your Mac or Windows. It's that Linux VM that Docker daemon controls and manages. The volume mounts keep everything contained within Docker's ecosystem. You'll understand this better when you see it in the demo. Another advantage is the portability between different Docker host environments. So unlike bind mounts where you cannot take your volume mounts across the different Docker ecosystem, if you're bringing it from Mac to Windows or Windows to Mac, you have to think about the way you've structured your shared paths. And there's better security isolation. Here's our test scenario. We'll create two Azure Pipeline agents that share storage. Agent 1 will build an artifact and save it to the shared volume. And Agent 2 will try to deploy that artifact in a later stage. This simulates real-world scenarios where you have a dedicated build agent and separate deployment agents. But they need to share build outputs without going through external storage. Let's start with our current setup. Two agents without persistent storage, then evolve to add the shared volume. First, we start with a Docker Compose up in detached state. We should soon see our agent come up online, and it's up. We will run our pipeline, and this is the pipeline we're running. Here we declare the variable TMP artifacts, and we're building an app called Hello World app and zipping that up. So our first stage is the build stage, where the build job uses the first agent, agent 1, makes these dummy application files. It creates these build outputs, zips it up, and save it into that artifact path that we've defined as a variable. Then in the deploy stage, it will use agent 2 to first list down what is in that artifact path and try to access that artifact path, unzip it, do a find command with a conditional if else to echo out an error if it can't find the artifacts. Here we can see that stage 1, the build stage, successfully added those dummy files and zipped up into our temporary artifact storage, and the deploy stage have failed with that error, build artifact is not found, because agent 2 cannot find the artifact in that shared artifact storage. Another way to prove this is to do a docker exec command into agent 1, do an ls into that TMP artifact storage, and we can see that it is in there where we have the hello world app zip. However, if we do the same docker exec command on the second agent, it's saying I can't find that file or directory. So this is expected. Artifact 1 is with the agent 1's temporary storage, but agent 2 has an empty directory. Each container has its own isolated file system. Now let's restart the containers and do a docker compose up, detached. Then check what the contents of the TMP artifacts directory where it can't find it. Gone. The artifacts have disappeared when the container was stopped and then started. And this is ephemeral storage in action. Now let's try and configure the persistent storage. This is what we're going to use. This Docker Compose would start with a broken one first. So I can point out an important thing here. So similar to the first Docker Compose where we have two agents, we just added this volumes definition with the Docker volume called shared artifacts and storing it on the local machine's disk. I want to point this out on Docker Desktop as well. So on Docker Desktop, that's the container tab. If we go to the volumes, you can see there's no volume in here. You can create it on Docker Desktop too. Another thing we added was for each definition of the agent service, we've mounted it this way with a volumes attribute and assigning the name of the shared artifacts. This is the Docker volume separated by a colon with a / shared volume, and this is the mount point for the container. So this / shared volume is the path inside the container. And this is a volume that Docker knows about. This is the volume name that Docker knows about. So both agent 1 and agent 2 share that same volume. Let's start it up. Stop our existing containers. We'll use this pipeline now with the persistent storage. And the only thing I changed here was the artifact path to be consistent with our Docker Compose definition of volumes with shared volumes / artifacts now to point to our Docker volume mount path. Everything else is exactly the same. Let's look at our error. So this one is saying that it tried to create it in that new Docker volume called shared volume, but it can't because of a permission issue. Let's now try and rebuild our containers with the fixed definition. So that command I just ran was to stop the broken one and use the other file that I called Docker Compose with volume and then build that, start those containers. Let's look at the Docker Compose file. The only thing we added here was, well, we use this Docker file with volume, meaning it's pointing to this Docker file to build the image. And the other thing was in the Docker file with volume, what we added here was this line to create the directory shared volume, change the ownership to the agent user, and give it permission over that shared volume. So after we've rebuilt the containers based on this new Docker file, we should expect this same pipeline to run successfully. So build stage worked. We can see that it was able to write those files successfully into that shared path, and the deploy stage worked as well. Deploy from persistent storage, where it was able to access that same Hello World app zip file, extracted it, and showed what the contents of those files are. So another way to check it is to run this docker exec command showing us what is the content of that shared directory. For agent 1, we can see Hello World app, and for agent 2, we can also see that shared path. Perfect. Both agents see identical content because they're sharing that same Docker volume. Oh, and one more thing on Docker Desktop. We should now see that volume we've created. And here I can see the artifacts folder with the zip file in there. So let's test the persistency by shutting this down, start it up again, and check the contents. And true enough, it's still there. The volume survives container restarts. Let's now try a complete rebuild of the entire image and recreate the containers. And it's still there. We can clearly see that as well on the GUI on Docker Desktop. The volumes still existed even after a complete image rebuild because the volumes are completely separate to the Docker image. So can I access the volume from my Mac? The only thing I can do with this is view, so read only view. And you can see that I can see some of the plain text in here, but that's about it. I can't do anything more but delete the whole volume on Docker Desktop. We can try with a Docker CLI by doing a Docker Compose volume to see what's the name of our volume. So I can do a Docker volume inspect and see the mount point here is this varlib Docker volumes persistent storage data. So I can try from my Mac and see if I can list that down, and it doesn't exist. As I mentioned earlier, I cannot access it directly from my Mac because Docker Desktop runs in a Linux VM. So this path for the mount point is actually in the Linux VM where my Mac does not have direct access to it. The volume exists in that Linux VM, not on my Mac. This is actually good for security. It maintains isolation between the host and the container storage. Let's now do a complete cleanup and test a fresh setup. Oh, it won't let me delete the volume because I still have the containers running. So what I need to do is stop those containers with a Docker compose down, then do a Docker volume RM. So that's deleted. We can see on Docker desktop that it's gone as well. Let's start the Azure agents again, do a Docker exec to check if it's there. And true enough, it can't find that artifacts subdirectory in shared volume. We look here, we can see that there's no stored data. It's gone. So now it's truly empty. And if I run the pipeline again, the deploy stage will fail because there's no artifact to deploy. So here I can choose the stages to run. I'm assuming that the build was there, but we're proving that after deleting our volume and restarting our image with that new volume created, the file's already gone. We know this is going to fail. And true enough, it failed. It errored out because it can't find that build artifact. Let's recap what we've built. Containerized agents that share persistent storage. We prove that with build artifacts that survive container restarts and rebuilds. And this is a foundation for build cache optimization and artifacts sharing. The key concepts we've learned are that volume mounts and bind mounts are types of persistent storage for Docker. We've learned of Docker volume lifecycle, where they outlive containers in general, unless you do a Docker volume RM command, which completely deletes these volumes. We've learned of mount points inside containers versus volume names in Docker. Again, volume name, it's what Docker uses to identify and manage the storage. It's like a label or ID. And mount path, this is where the volume appears inside the container's file system. The setup that we did can reduce build time significantly through cache persistence and eliminate the need for external artifact storage in certain scenarios. You get the best of both worlds with fresh images each time your container restarts, but have persistent storage to store build artifacts to optimize and speed up your deployments. The goal is not to make everything persistent. It's to make use of persistent storage where it adds value while maintaining the benefits of containerized builds. Thanks for watching and happy building!